Oh, hi everybody, this is Catherine. Today we're going to walk through the question 230, Kth smallest element in the binary search tree. This question comes from the list of top interview 150 on legal. Okay. Given the root of a binary search tree and an integer k, return the kth smallest value of all the values of the nodes in the tree. Um, and we need to notice that um the kth smallest value is one index. Okay. So before we get started, we need to clarify what BSC is. So binary search tree means in a binary tree, the for the root and its children, the left child of the root must be smaller than the root's value, and its right child must be larger than the root's value. And also for every single node, like for all the subtrees rooted at every single node in that tree, like they must be like binary search tree as well. Anyway, okay. So given that rule, um, after like going through the examples given, I didn't see any equality cases, so I'll just ignore that part. I'll just assume that only like I'll just like take inequality constraints into account. Okay, so let's move on to the first example. Um, with that rules, like a nature of binary search tree, we can easily tell that, not easily, but it's not hard for us to find out that with a pre-order traversal, which means left child, root, and right child. So with that order, we can sort the values of all the nodes in a binary search tree in ascending order. So for example, here, um, if we use pre-order traversal, we'll start from the very left bottom. So here, node 1 does not have any left child, so we'll just move on to the root itself, which is 1, and then we will go to its right child, which is 2, and then move up to 1's root, which is 3, and then we'll go to 3's right child, which is 4. So with that pre-order traversal, we can get a list of node values 1, 2, 3, 4, which is absolutely in ascending order. And I believe the second example follows this rule as well. So yeah, and that means once we traverse the binary search tree with pre-order traversal, we can easily find the kth smallest value with index axis, right? So yeah. Oh, and then we can just move on to the coding part. So before everything started, how can we do a pre-order traversal? Um, we can do a DFS like helper to help us do this traversal work, right? So sorry for saying so many souls. Yeah. So we can define a helper function. Let's just call it DFS. Um, oh, sorry. For pre-order traversal. Okay. So for this helper, we'll take in self, absolutely. And then we'll take in the root, which is the whole tree. And then we also need uh like uh an array to record all the nodes in ascending order. So let's just call it path. Okay, so yeah, and path is a list. Yeah. Okay, so for each DFS, we need to consider the edge case, like the base case first, right? So what if the tree is null? If not root, we'll just return nothing. Um, yeah, and then we can move on to the real traversal part. So for the left child, uh we'll just recursively call the DFS helper. and also continue like recording all the values into the path. And what if we encounter the root itself? We'll just add the value to the path. So path append the value of root. Okay. And we'll do the same thing on right child as left child. Just call the function recursively. Okay, cool. So yeah, we've just done the helper. And then we can continue, like we can go back to the main function. Um, Before we call our helper, we definitely need to declare a list. Let's just call it path. And then we can just call the helper. Root is root and path is path. Okay, then after this, we have, so after all the like recursion part completed, we'll get our path list updated full of all the node values. And then we will continue to look for the kth smallest value. So if the k, like I mean the kth smallest value exist, so if k is larger than the length of path, we can then return it. Remember that the k smallest value is one index, but in Python, a list is zero index. So the k smallest value has an index of k minus one. And what if the k does not even exist, or like it just go beyond the list? We'll just like, oh, sorry, if k is smaller than n equal to, sorry. And what if the k just does not exist? We'll just return a -1, uh, representing like invalid parameter. Okay, cool. So we can try to run the code. Yeah, so it's just accepted. Um, and we'll just try to submit it as well. Okay. So in this problem, the runtime complexity, um the runtime complexity is O(n), where n means number of nodes in the tree, because apparently we like visit every single node in the tree. And for the space, I'll just call it O(n) as well, because we use a separate list, which is a new data structure. And also we use recursion, so the height of the recursion stack takes some memory as well. So yeah, thank you. And this is a medium problem. Yeah.